Welcome back, folks. We're looking for a short video here, and this video is going to show us how we convert between the three different forms that I introduced in the previous video, okay? Rectangular, polar, and exponential form. So I'm going to start with that same point on the complex plane that we used in the last video, and then I'll end up doing one more example just to make sure that we got our heads in the right space. Okay, so here's our point. Okay, and I have it set up as polar, so I'm really starting as moving from polar to rectangular. And polar and exponential are so similar, right? So we can think of this point as 5 at an angle of 36.86 degrees. And we could represent the same thing as 5EJ 0.643. That's the same angle, it's just in radians. Okay, and they really have the same information. So if we want to generalize this, we can do that. And we can say, well, the polar form has some value capital A at an angle of some angle theta. Okay, and that's going to be equivalent to A e to the j theta. Okay, so they have the same information. They have the distance directly from the origin to the point on the plane, and they have the angle. So if we want to convert these, we can do that. Okay, we want to get down to the rectangular form. And in the rectangular form, we're finding the two components that are along each axis. So we get the real component there. Okay, we know what that is because we can read the plot and we saw the previous video. And we get the imaginary component there, parallel to the imaginary axis. But the point isn't always nicely, on nice round numbers. It just doesn't happen all the time. So we have to be able to convert. Okay, most of the time I'm going to use a calculator or a computer to do this for me, but it's good to understand that it's really just trig. We're just doing trig. Okay, so we might call this real part A, okay, along the real axis, and we know that that's going to be 4 in this example, and we might call this imaginary part B, and that's along the imaginary axis. Okay, so we would represent this in rectangular form as A plus JB. Okay, so how do we do that? We really just use trig to move between those. So we know the angle, we know the direction, and we're just going to use sine and cosine to get us there. Okay, so the value for A, that's going to be the adjacent angle. So I'm going to use a cosine, and let's say the adjacent over the hypotenuse, well, the hypotenuse is just going to be capital A, right, is equal to the cosine of the angle. But more often than not, since we know that piece of information and we're looking for A, you're going to multiply both sides by A, right, and just bring that up here, capital A. And this is lowercase a on the left. Okay, it's that simple. That's just a little bit of trig. Okay, we're going to do the same thing with B, but B is now the opposite, right? So it's going to be the opposite over the hypotenuse. So that's going to be sine of cosine, or sine of cosine, sine of theta, there we go. And then we do the same game, right, where we already know what capital A is. So I'm going to bring capital A up there and just get that a little closer. And that's going to give us our two components in rectangular mode. It's honestly that simple. Okay, so if we know those values, we could say A is equal to 5 times cosine of 36.86 degrees. Make sure your calculator or computer is interpreting that as degrees. Make sure you're in the right mode. Okay, and we'll find that that is equal to positive 4. Okay, and here's B, and we can say that's 5 times sine and the same angle. You can use the radian one, just make sure you change the mode of your calculator, and you'll find that that's positive 3. Okay, so we can put that together and say that that point, okay, let's see here, let's grab these guys. Okay, we can take these, and now we can say it's equal to 4 plus j3, using those components in this form. Okay, I'm hoping this is review, but if not, you got to know it. Okay. Okay, so moving back the other way. Okay, now we know 4 plus j3. How would we go back the other way? We want to get that back to this form. And again, it's just a little bit of trig, right? We would say, well, what is A? And it's still a right triangle, right? So let's say, come on, right for me. There we go. Back to polar. Right? And we would say that A is equal to the square root of lowercase a squared plus lowercase b squared. Okay, so that's the real component and the imaginary component. You're just doing Pythagoras to get you there. Okay, here's the one where you're going to get in trouble. Okay, theta. And we need the inverse tangent. Right, because we get the opposite over the adjacent, and that's going to give us the angle. But I'm going to do an example where if you're not paying attention, you'll get the wrong angle. Okay, so that's B over A. All right, so using our example here, we're going to say A is equal to the square root of 3 squared plus 4 squared, which of course is 5. It's a 3, 4, 5 triangle. So I was nice to you there. And here we'll say theta is equal to the inverse tan -1 over, okay, so it's the imaginary component. Just don't get them flipped around. It's the imaginary component over the real component. So it's the inverse tan of 3/4, and that's going to be 36.86 degrees, also known as 0.643 radians. Okay, just behind my head there. Okay, so we can move back and forth between them with trig. Let's think about this example. I'm going to have to hand draw this one. Ready? Here's our complex plane. And we have a real axis and an imaginary axis. And I'm going to put a point out here. It's going to be right there. Okay, it's going to be -18 minus j4. Okay, so we want to get the polar form like this. We want to know the direction from the, or we want to know the distance from the origin and the direction, right? We might naively go about this and say, okay, let's say A is equal to the square root of -18 squared plus -4 squared. Okay, I haven't actually done that. I'm going to pull out a calculator here, and we're going to go ahead and do that. So we're going to get -18 squared plus -4 squared. Okay, we're going to take the square root of that. And we're going to get 18, I'm rounding a little bit, 18.44. Okay, whatever unit it is, whatever we're measuring with this. It could be volts, it could be amps, it could be meters. It represents something in the real world. But right now it's just 18.44 unitless. Okay. And, you know, that feels about right because this part's 18, so we know it's got to be a little further than 18. So 18.44, yeah, you know, it passes the gut check. Okay, here's where you get into trouble. Okay, theta equals the inverse tan. And let's see, we have the imaginary component, which is -4, over the real component, which is negative 18. Okay, I'm going to check the mode of my calculator. I'm in degree mode. And I'm going to do negative 4 over negative 18. And I'm going to take the inverse tangent of that. Go. And I will get 12.529 degrees. Okay. Now, I try to picture these in my head because I don't use these every day. Okay. I probably use them more than most people, but I still don't use them every day. So I try to picture this in my head. Does this look like 18.44 at an angle of 12.529 degrees? Okay, it doesn't look like it to me, and here's why. That 12.529 degrees exists right there. Okay, that's 12.529 degrees. But what we're interested in when we're representing these using complex numbers, we're interested in this one. Okay, that's what we want for theta. So we have to consider what quadrant it's in. And you probably learned this at some point and then completely chucked it out of your brain when you didn't need it anymore. And we got to be a little careful because we would end up with a representation that's not true. Okay, so this is not true. We would mark that wrong. We have another 180 degrees, right? So I really have to take that, and because it's in the third quadrant, I have to add 180 degrees. Okay, I'm hoping you've learned this before, and I'm just jogging your memory. Okay, we don't want that little angle. We want this big one. So just add 180 to it, which is going to be 192. 192.529. Okay, now I'm going to nitpick that one because I can. By convention, we try to keep our angles between plus and minus 180, just so that they don't get overly large. So you'll often see this with the equivalent angle, which is really just this angle here, right? Which is going, so I'm going to take 192.529 eventually, plus 180, okay, and I'm going to subtract 360, and that will get me the equivalent 18.44 at an angle of negative 167.471 degrees. Okay, and that would be the preferred form. It locates the point in space correctly. This one wouldn't, right? This would put me somewhere up here, and I don't want that. I want to get to this point in space. Negative 167.471 degrees. Okay, so I'm headed out in this direction, and then I take 18.44 steps out, and I'm at the right point. Okay, so just be careful. If you're doing this by hand and you're using the inverse tangent, think about what quadrant you're in. When in doubt, draw a picture, or at least use your brain to picture it in your, in your imagination, and make sure it passes the gut check because it's important. Okay, this is conversion between polar and exponential and rectangular and going back and forth. I hope this is a good refresher. I want to get to the meat of this. I want to start talking about why complex numbers are important, and that comes down to the operations that we do to them. Okay, so stay tuned and good luck.